So what we're going to do is some of these questions have we've actually done before, so I will be sometimes going a bit fast, but when we get to the questions that I know that people struggled on, I will slow down a little bit. So let's start with question 1. So the first question for question 1 asks, in the circuit shown in figure 1, the battery of an EMF, so this battery here has 6 volts and has negligible internal resistance. Now this part is probably one of the most important bits of the actual thing, because it tells you that there's no other resistance in that circuit, and you'll be doing internal resistance next week. So they're asking currently when the switch is open, so the current would flow like this. It will go all the way around and up like that, okay? So this means that the total resistance of the circuit is going to be 20 plus 60, which is 80 ohms. The total voltage is 6. So V equals IR. So 6 equals something, the current times by 80. So the current equals 6 over 80, which equals a grand total of 6 divided by 80, which is 0.075 or 75 milliamps. Okay, and I did see that one done quite well. Please remember your units on this one. So you got the milliamps on here. There was 1 mark here for actually getting the total resistance correct. So there's 1 mark here, and there was 1 mark for getting the current correct here. Now, this one was, some people fell down a little bit on this one because they didn't clock what was happening. Now, the switch is now closed. Now, electrons always take the path of least resistance. So when it's closed, so electrons take path of least resistance, what they're going to do is they're going to do this. They're going to go up here, and when this is closed, it's going to go down here. No current or very, very little will actually go through this section because it's got resistance, and the electrons rather go around the switch, which has 0 resistance. So there'll be no current in the 60 ohm resistor. So the total resistance of the circuit is 20. V equals IR. So 6 equals I times by 20. So 6 over 20 equals I. So 6 divided by 20, which is 0.3 amps here. And again, there was 1 mark. So there's only 3 marks available for this whole thing, and you could have picked them up from all sorts of places, but there was 1 mark here. So you can get 4 marks. So you could have got, the other mark was for this, but you can only get a maximum of 3 marks in this question. Now, what it says here, the switch is now replaced with a voltmeter. So what's actually the circuit's going to look like is the circuit's going to look like this. There's your ammeter. There's your 20 ohm resistor. There's your 60 ohm resistor. There's that, goes back up here. This is 6 volts. And there's now going to be a voltmeter across here. And this has infinite resistance. Okay, so this means that current won't flow. So they're asking for the reading on the voltmeter. So they want the reading on the 60 ohm resistor. So a little trick here, you can of course do the VIR, the total resistor A, resistor B. So this is BA, this would be B. And you know that this is 6, you know, because this current's going to go this way around. Oops. You would know that would be 80. So this would be, of course, 75 milliamps. This is 20. This is 60. It's all in series. So this is going to be 75 milliamps. This will be 75 milliamps. So you can work it all out. 20 times 75% to the minus 3 is 1.5. And so 6 minus 1.5, that's going to be 4.5 there. So you know that 60 times by 75 times 10 to the minus 3 equals 4.5 volts, and that was the mark there. So 2 marks, one for realising how the circuit was formed, or the current, and 1 for the answer of 4.5. Okay. Okay, scrolling down to question 2. So again, this word here, negligible internal resistance. This is actually probably one of the most important words again. So this means there's no extra resistors anywhere that you've got to consider. Okay, so what they're asking here is the voltage across each lamp. So you've got 15 volts and they're all the same resistance. So they're all going to have an equal share because of V equals IR. They all have the same current. They all have the same resistance. And I know the volt potential across this one, the potential across this one, the potential across this one, they all have up to 15. So it's just literally going to be 15 divided by 3, which is going to be 5 volts. Or you could have done the total resistance is going to be 36 ohms. So you've got V equals IR. So you can have 15 equals I times by 36. So I equals 15 divided by 36, just to prove it all works, is 0.42 amps. And then you could have gone, okay, so the voltage in the 12 ohm resistor is going to be 0.42 times by 12. So times the answer by 12, and you end up with 5 volts. So that was one way you could have done it. You could have done it a really long-winded way, but it's up to you. So this method here is they are all the same resistance, so equal share of PD, or you could have done it that way. It didn't really matter. The thing is, if you did it the other way, you would have worked out the next question. So this is only worth 1 mark here. Okay, so the 5 volts is worth 1 mark. Calculate the current through the lamps. Well, exactly what I've just done there. So the total resistance is 36 ohms. The total voltage is 15 volts. I can't write 15 at all. V equals IR, so 15 equals I times 36, so I equals 0.42 amps. Okay, so this is going to be 1 mark for working out the sort of doing this sort of maths here, and then there's 1 mark for the answer of 0.42 amps. So it's now 2 lamps are now disconnected and reconnected in parallel. Another way this could look, this circuit could look like, is this circuit could look like this. It could have 15 volts here. It's exactly the same circuit. So this is 12 ohms, this is 12 ohms, 12 ohms, and then 15 volts. Exactly the same circuit. It's just another way of drawing it. So it means that this section here, that's in parallel. And that is in series with that. So I'm going to call this section A. So the resistance of section A is going to be 1 over 12 plus 1 over 12, which equals 1 over the resistance of A. So 1 over 12 times by 2 is going to be 1 over 6. So the resistance of A is going to be 6 when we've got to flip that round. So this means that I could replace this whole section here with the 6 ohm resistor and I'll get the same current. So what it means, it now looks like I've got 6 ohms here and 12 ohms there. And that's my circuit. I need to work out the current. So the total resistance is going to be 18 ohms. V total is still going to be 15 volts. So I've got 15 equals I times by 18. So I is going to be 15 divided by 18, which is going to be 0.83, which is exactly what they were trying to find here. It was trying to prove that it was 0.83. So to get this one, to get the marks, you needed to work out this section for 1. And actually doing the maths here was the second part here. Hence show that the current in each lamp is the same as the current in the lamp in figure 1. Again, hence show the current in each lamp is the same as the current in the lamps in figure 1. Okay, so what they're trying to do here is they're saying that the current that's going through the lamps in this one, so the 2 lamps here, is exactly the same as the current that is going through when it's in series. So what I'm going to do is I'm just going to, I know the total current, so if I could just quickly draw the circuit here. So the total current, here's my 12, here's my lamp, here's lamp, that one there. The total current is 0.83 amps, and I'm trying to show what the current going in these lamps is. So what I know here is that I've got 15 volts, and this is 0.83. So what I'm going to do is I'm just going to label these A, B, and C. So I've got A, B, and C, and V, and I'm going to delete that. Make that a little bit lower. So I've got V, I, and R. I've got the total. I've got A, B, and C. I know the total is 15. I know the total resistance, because we worked it out before, is 18. I know the current is 0.83. I know that is going to be 12 ohms. That's going to be also 12 ohms, and that's going to be 12 ohms. But the current's different. So this has got 0.83 going through it. So I can actually work out what that has. So 12. So the voltage on A is going to be 12 times by 0.83, which is going to be 12 times 0.83. So that's going to be 9.96 volts. So it's going to be 9.96. So the voltage on B, of course, remember Kirchhoff's law. So the voltage can either go this way around or it could go this way around. Okay, but either way, it's got to equal 15. Okay. So the voltage on B is going to be 15 minus this 9.96, which equals, so 15 minus the answer, going to be 1.51. Right. 15 minus 9.96. 15.04. I'm just going to double check something. 12.0843. Yeah, 9.96 and then 15 minus that. Yeah, for 5.04. Sorry about that. It's going a bit weird, my calculator. So 5.04 volts. So that's going to be 5.04. And this is also going to be 5.04. So the current through, so you know this is 5.04 equals I times by 12. I equals that divided by 12. So it's going to be 0.42, which is exactly what you were looking for. So this answer here is exactly the same as the current before. So to get this mark, you got, again, it's only worth 3 marks, I believe, this whole thing. They literally just wanted you to do the maths for 1, and that was all it was worth. So it's quite a lot of work for 1 mark, but they've given you a lot of the information from before. And remember, you can, in any circuit, you can sit here and you can change it, etc., like that. Okay. So how does the brightness of the lamp compare with figure 1, figure 2? So brightness is related to power. So that's going to be P equals IV. Since they have the same current and the same PD in each circuit, and you can see that from what you did with your maths, you can see that they're going to have 0.42 amps, so they're going to have about 5 volts here, and in this question they're going to have 5 volts and 0.42 amps. So in each circuit, they have exactly, since the same current, and so in each circuit, they will be the same brightness. Ooh, Sarah can't spell. So how does the compare with the brightness of the lamps 1, 2? So this is like kind of a state and explain one here. Sorry, I just got to find my pens. You get 1 mark for saying they have the same brightness. You could have had a random guess. And you got 1 mark for saying, basically explaining why you believe that. The fact that they have the same current and the same current each second. I've backed out with using P equals IV there. So that was question 2. Again, this is just using, there wasn't much potential dividers in this question. It's actually a lot more to do with reminding you how to do circuits. This one, however, was potential dividers, and you've actually seen this one before, and it's a lot of going back in the question. Okay, so let's actually go through this one. So when the thermistor, so this one here is a power supply with, again, negligible internal resistance. This, again, is important. The resistor has a resistance of 67 ohms. When the thermistor is high, the potential difference, we're going to count the potential difference across R. So using table, so we've got V, V, I, and R. I've got total, which is 12 volts, and I've got, I'm going to call that R, which is 67, and I've got the thermistor, which I'm going to call A there. Okay, and I know A has got 4.5 volts across it. Okay, so I know that the total voltage is 12, which equals the voltage of R plus the voltage on A. So the voltage on R must be 12 minus 4.5, which equals, can't even think of maths today, 7.5 volts. There we go. So it's going to be 7.5 there. Okay. So it then asks what's the current in the circuit. You can do it from any section you wish to now. So you know that the voltage of the resistor is 7.5. You know its resistance of the resistor is 67. So V equals IR. So 7.5 equals I times by 67. So I equals 7.5 divided by 67, which is 0.11 amps. Please remember to please put your answers on here. So this was the first one was only worth 1 mark here, and that was literally just for a subtraction. This one was worth 1 for this and 1 for the sum there. Okay. So what they're asking here is that the thermistor changes to 25 degrees and its resistance is now 360. So what the circuit looks like is this now. So I've got 67. This is now 360 ohms. And this is still 12 volts. It wants the potential difference across the thermistor. So you're trying to find, let's take a voltmeter here, what's it going to be? So the total resistance is going to be 67 plus 360, which is 427. The total voltage is going to be 12. So V equals IR. So 12 equals I times by 427. I equals 12 divided by that is 0.03. And then, of course, you can work out the thermistor. So that's going to be 0.03 times by 360. Which is going to be 10.11 volts, which is exactly what you were looking for. So there's 1 mark for that bit. 1 mark for trying to, you could do the potential divider formula if you wanted to. So you could have used the V1 or VA equals completely got V total times by, I don't use this one very often, do apologise. So the voltage of here was V total times by the 360 over 360 plus 67 there. So you could have done 12 times by 360 divided by 360 plus 67, and you would have got the same answer here, because that is the resistance of A. So it would be VA equals V total times the resistance of A over the R total, which is acceptable to use. But I don't like using that. I just prefer working out in steps, which is perfectly acceptable as well. So you got 1 mark for that, 1 mark again for another method, and 1 mark for your answer, 10.1. Calculate the power dissipated in the resistor when the thermistor is at 25 degrees C. So this one's important, give the appropriate unit for your answer. So there are 3 units on this one. Okay, so if we go back down here, so they want a unit. So P equals IV. So we know the current is going to be 0.03 times by the potential of 10.11. So it's going to be times by 0.03. We get an answer of 0.3 watts there. Okay. Oh, resistor. Oh, sorry, I should actually read the question. Do apologise. I was sitting there going, that doesn't look like I'm asking. Okay, so it's resistor R. Do apologise. So you can, that was a mistake I made. So this is resistor R. So you've got the voltage of R here. So that's I times by 12 minus 10.11. So that's going to be 0.03 times by 12 minus 10.11. That was my fault there. 1.89. And that equals times by 0.03, 0.0567. Okay. So that's going to be 0.0558 there, watts. Okay. So if you actually read the mark scheme, there's lots of things that they could allow. They could allow different voltages, etc., how much they're allowing for this. There's a lot of flexibility. But there are 4 marks available. 1 for the method that you use here, 1 mark for actually doing the maths, 1 mark for the numerical answer, and 1 mark for the unit of watts. Or they will allow joules per second. That is also acceptable as well. Question C. The circuit is modified with a 570 ohm resistor here. Now, this is the one I saw a lot of people go, I don't know how to do it. This here means that the thermistor is 360 ohms, because you had that from the question before. So this section is in parallel, and this now. So the circuit is now here, work out the current in the 67 ohm resistor. So you're trying to work out here the total current. So this here, we're going to call this section A. So the resistance of A is going to be 1 over RA is going to be 1 over 360 plus 1 over 570, which is going to be 1 over 360 plus 1 over 570, and then 1 divided by that. So that answer, by the way, that's going to be 4.5 times 10 to the minus 3. So the resistance of A is going to be 1 divided by that, which is going to be 220 ohms. So the resistor R plus R of the A. So this whole section can be replaced with a 220 ohm resistor. It's going to be 67 plus the 220, which is going to be 287. And then V total is going to be R total plus R total. So it's going to be 12 equals I times by 287. So I equals 12 divided by 287, going to be 0.04 here. Uh, 0.042 if you want to be a little bit more exact. Okay. So 0.042. So again, this is quite a few marks. There was 1 mark for doing this section. There was 1 mark for this section. 1 mark for doing this maths here. And of course, as usual, 1 mark for the answer there. Okay. So explain in terms of charge carriers why the resistance decreases as the temperature rises. So 3 marks, so 3 points that you want to say. So as the temperature increases, more charge carriers are released. Okay. This means more charge carriers in circuit, so more current. Therefore, to respect V equals IR, if the total V is the same and I increases, R decreases. Okay, so basically what I'm saying here is I'm literally going, well, I know that it says explain in terms of charge carriers, so this section here, that's what I've done here. I've literally explained that there'll be more carriers released. I've explained that that more carriers in the current, so there's more current. And then I've actually mentioned here that the fact that to respect V equals IR, if the total of V is the same, and in the whole circuit, nothing else has changed apart from that thermistor, the total R must have increased somehow. Okay, question 4. Now this is a new question we haven't done yet. So this is a nice one because it actually gives you the graph for temperature and this is actually quite interesting to realize that this letter here, phi, equals temperature. You will be using it later on. Okay, so they've got a nice setup of a variable resistor and a thermistor with a voltmeter across it. First question, explain what's meant by a potential divider. A circuit with 2 or more resistors that split potential. Okay, quite a simple question. It's a standard question they like asking it. I think they ask it in the next question as well. But it's just basically it's a circuit with 2 more resistors that splits potential. Okay. So state and explain what happens to the voltmeter reading when the resistance of R is increased while the temperature is kept constant. So this is important. The temperature is kept constant. So that means the resistance of the thermistor is constant too. Okay. So state and explain. Again, this is important. State and explain. It's worth 3 marks, this one. So state and explain. So you got the state mark and then you've got your explain. So this is the state part. So what will happen to the voltmeter I as it is increased? Our potential will increase. Okay. since V equals IR, if R increases, if R increases, its PD increases. And since the total potential is the voltage of R plus the voltage of T, if the voltage of the thermistor is not changing due to resistance, the voltage of R has a bigger share. Okay, so again, this is just 3 marks. So you get 1 mark for stating the obvious, and you can always have a guess at that one, so it's really important. 1 mark for this kind of explanation here. And then this one here. So my answer comes actually from the alternate. So the other one remains constant. So the actual V of the thermistor and R2 remain constant, which means that the actual resistor of R is going to increase. Okay, so my answer is actually a little bit of the alternative as well as the normal. But what I've done is I've stated what will happen. So R's potential will increase. If you didn't know, you could, when it was state and explain, you could always have a random stab in the dark, up, down, or stays the same. And explanation, I'm just trying to explain that, well, since R has increased, its potential increases because of V equals IR. And since the total is the voltage over the resistor plus the voltage of the thermistor, if the voltage of the thermistor is not changing due to resistance, VR has a bigger share. And that's me explaining that one. Now this one, it says, it's don't explain what happens to the ammeter reading when the temperature of the thermistor increases. So again, state and explain. So I'm going to state what happens. So this is my state here. So what's actually going to happen is as the thermistor gets hotter, its resistance goes down. So if its resistance goes down and the other resistor stays the same, I've got less resistance in the circuit, which means my current will increase. Okay, so here that was my statement. My explanation is exactly what I just said. The resistance of thermistor decreases. So total R decreases. And since V equals IR and V is the same, I must increase. Okay, so you got 1 mark for stating at a higher temperature resistance is lower. Okay, obviously the resistance is lower, so the circuit is lower and the current increases. So you get 1 mark for the actual increasing bit and 1 mark for mentioning that the fact that the resistance would be lower here. So stating is telling me what would happen, and this mark here is the explain. So the battery here has an EMF of 12 at 30 degrees, and the resistance of the thermistor is 2.5 times 10 to the 3 ohms. And the voltmeter is calculate the voltmeter is replaced with an alarm that has across it. So let me actually just draw the circuit just to make a little bit more sense of what the hell is going on. And that you can do that, that's absolutely acceptable here. So this is again 12 volts here. This is currently 2.5 times 10 to the 3. And now it's got an alarm across it here. So speaker looks like that. That activates on it. So the alarm that sounds across it when the voltage is across 3 volts. So they actually haven't given me, they told me to find what R was. Okay. I've picked up the 67 from last thing. So let me just draw it like the one on the top of the question. I forgot this was a slightly different question. So this is my R, and this is my speaker here. And currently this is 2.5 times 10 to the 3 at 0 degrees C. Okay, and it wants the resistance R that will cause the alarm to sound when the temperature is lowered to 0. So I want across this one, so I'm going to call this T. So across T, I need 3 volts when the resistance is 2.5 times 10 to the 3 ohms. And the reason I know that is it says here, calculate the resistance R would be to the alarm to sound when the temperature of the thermistor is lower. So when it gets hotter, this resistance actually decreases. And because of V equals IR, this is going to get less and less and less potential. So I want at this point here to have 3 volts for it to turn on. So when it gets hotter, so when temp increases, R decreases. R of the thermistor decreases, which means the also decreases. So I'm just going to find out this point here. So there are numerous ways to do it. So this is 12 volts. The way I would have done it is that if the 12 is the voltage on the resistor plus the voltage on the thermistor, so that's going to be 12 equals 4 voltage on the resistor plus 3, so that's going to be voltage of the resistor is going to be 9 volts. I can work out the current quite simply at this point. So the voltage of the thermistor is 3, which equals the current times by 2.5 times 10 to the 3. So the current is going to be 3 divided by 2.5 times 10 to the 3. So the current is 1.2 milliamps. So now I know the voltage in the resistor is 9 volts. I know the current in the resistor is going to be 1.2 milliamps. And therefore I know V equals IR. So 9 divided by that, and I get an answer of 7,500 there. So it's worth only 2 marks. You get 1 mark for your method and 1 mark for your answer. It's a bit of a long-winded way of doing it. There are other ways you can do it, but I'm just breaking it down into small chunks. So one change you'd make to the circuit, so the alarm turns on when the temperature falls and it gets hotter above a certain value. Well, the easiest way to change it is to change the position. So it is over R, not the thermistor. Okay, and the reason for that is, as I said before, is that as this gets hotter, this resistance is going to go down, which means that the this resistance here goes down, which means this gets less voltage as it gets hotter. And if this is getting less voltage, this will be getting more voltage. So if you change it over to the other resistor, when it gets hotter, this will get more potential and eventually turn it on. Okay, you will probably need a much lower resistor though, but the question wasn't asking for that. All right, last question. So this one is the one that actually was interesting because I saw a lot of people struggle, especially with the last one. Okay, so again, electrical potentials, that again, this negligible internal resistance, one of the most important parts of this whole thing. You have to see that to assume there is no other resistor in that circuit. So it shows an electrical supply circuit with between 4 and a variable resistance between 0 and 8. State this type of circuit. This is a potential divider. Nice 1 mark question if it ever comes up. This is a potential divider question. Calculate, so this is the question that stumped a few people. Calculate the minimum and maximum potentials that could be obtained across X and Y. So if you think about it, this resistor here, so I'm going to call this A and I'm going to call this B. Okay. B can either have a maximum or a minimum, and it's asking you for the maximum minimum across the actual A. So it's looking for the V max and min of A. So if you think about it, this with B can either be 0 ohms or 8 ohms. So B, the resistance of B is either 0 to 8 ohms. And of course, at 0 ohms, the voltage of B is going to be 0 volts. So if there is 0 volts across B, there is going to be literally no potential across it, which means that the A is going to get all of the potential. So the maximum it's ever going to get is 12 volts. The part A will be 12, and that is when the resistance of the variable resistor is 0. When the resistor is 8, that's a little bit different. So at the 8 part, I know the total resistance is going to be 4 plus 8, which is going to be 12. Okay, so 12 equals I times by 12. So the current is going to be 1 amp. That's quite nice. Which means across the 4 ohm resistor, so we're going to call that the V of A, it's going to be 1 times by 4. So that's going to be 4 volts. So this here is going to have, this resistor here is going to have between 0 and 8 volts across it. And you actually see that would make a lot of sense because this resistor here, B, is going to be much bigger than A, so we'll have most voltage when it's at full whack. This question here is worth 4 marks. So you get 1, 2, 3, 4, and a lot of space for working. But again, this is just getting you to think of Kirchhoff's voltage law, and Ohm's law, how voltage is shared between 2 objects, and how Ohm's law dictates how much of that share is going to go over V equals IR. These last 2 questions is where I saw a few errors. So it says, this one here is complete the circuit diagram to show how the potential can be adjusted. So the relative loudness can be adjusted. It's a bit of a weird one. What they're actually after here is a circuit that literally looks like this. Okay, because what this means is depending on where this arrow is. So the arrow is a scale. Okay, and that affects how much current ends up going through it. So it will depend on how much current is going through this section and this section. Okay, so at the moment it's like a 50-50 split. So what will happen is that the current that goes through each section is quite nicely split. But if you move this arrow backwards and forwards, it starts to show those. So the arrow is a scale. So depending on where it is, changes the resistance either side. So what you end up with is actually a circuit that looks more like this. And what happens is the arrow dictates A and B. So the arrow changes the value of A and B. So what happens is this arrow sort of slides across and it will continually change the value of A and B, which would then continually change the current going through each of these speakers, which would then, of course, change the potential across it, because it all depends on V equals IR on this one. Okay. Now, this is one of the questions I didn't see answered very well, and it's explain the advantage of using a potentiometer across over the 2 resistor arrangement in figure 2 for this purpose. So explain the advantage of using the potentiometer over the 2 resistor arrangement of figure 2 for this arrangement. So the whole idea is that these two, what happens if you change the potential difference, you change each of the speakers individually, so you change the current that's going through them, and therefore you change the volume because P equals IV, okay? So one of the problems, there's a couple of things here, and that actually links to the first question. If you go back, this actually is the first section here. And as you can see in figure 2, okay, you actually only have, you have a limited range on each speaker. And that is because if I actually go to the top here, this is exactly like the first question, which was this one. So this is the first question, and you had the 4 ohm resistor and you had the 0 to 8 ohm resistor here, and you were checking out the voltage across that section there. And you knew that this resistor can either go from 4 to 12 volts across it, okay? This can go from 0 to, I believe, 8 volts. So the thing is, there's a limited range. This one here, they're not equal ranges at all, okay? So this is the problem, is they have different ranges. So figure 2 has a limited range on each speaker, which are different for each one. Okay, so these are actually completely different for each speaker, which is a big problem. Whereas in this arrangement here, what you can do, because they're connected to the same resistor, you can actually pull it across that literally nothing will flow through this circuit here, or everything will flow through this one here. So if you set up, so if I explain here for each one, okay, so what I can explain to you here is that you can have a setup like this. Oh, I'm really bad at drawing speakers. You have a setup like this, which would be max, so this is A and B, so max volume on A, okay? Or you can, of course, do it the other way around, where you have the circuit that looks like this. Yep. So, oh, I do apologise, not max volume on A, because let me just delete that. Because what's actually going to happen here is that all the current, because I've got to delete all the stuff. It's actually not max volume on A. So this is method 1 you could have. What will happen is the current, of course, will take the path of least resistance. So all the current will go through here. So that's all current will go through here. So the maximum volume will actually be on B. Okay, and on this one, all current will go through here. So the max volume is on A, on this section here. Okay, and it's all to do with all current. Okay, it's all to do with being the path of least resistance. This is method 2. Okay, so you can actually have the same volume in each one, and it will incrementally change on each side. So this one here, this section here is, say, equal volume, because it's in the middle. So this one, actually, you can share these equally. If you look at this one here, this object has, number A has a 4 to 12 on this one, and B has a 0 to 8. They have completely different ranges and different volumes. A bit of a hard question. Didn't see it done very well at all. So you would actually have got 1 mark for mentioning that you would have limited range on each speaker, and then the fact that you've realised that each speaker would have different ranges completely, which is an absolute nightmare if you think about it. This format here, what I've shown you here is how figure 1 is better. just to prove to you that you can actually have a section here where you have all the current. So you would turn off A. So A is off, and this one will be B is off here. And you can actually see that you got all the current here. Bit of a difficult question. It's actually a second year paper question, this one. I took it from a year 2 paper. Okay. So there you go. That is the potentiometers questions from this week. Next week, I'm going to go through some resistivity questions. I'm also going to post out a Google form to see if this will be better at a different time, and if you want me to go through anything else, okay? Yeah, so that is, if anyone's got any questions, please drop me a line and I'll go through that, but I will upload this whole sheet so you can actually see it on, and all my notes on Classroom in a few minutes. Okay, guys? All right. Have an awesome day, an awesome week, and I'll see you soon. Take care.